All right, good morning, everyone. Let's get started. So today we talk about compaction and curing. When we design a concrete, we mix the concrete and we cast the concrete in place. Okay, and we also need to compact the concrete, finish it, and then we cure the concrete for around 1 week or so. Okay, so today we talk about the last two steps: compaction and curing. Okay, so the reason we compact the concrete is to get rid of the voids and entrapped air. Okay, so entrapped air, remember, is the bad air, which is in the millimeter size. Okay, in the concrete, not on purpose. We also have entrained air, which is added by adding air entraining agent. Well, one type of the chemical admixtures. Entrained air is good air, but entrapped air is the bad air. Okay. And also to fill every corner of the formwork and also around the reinforcement. Okay, so that's the reason we need to compact concrete. We could use external or internal distribution. Okay. Typically, depending on the job, around 5 to 20 seconds. When the workability of concrete is lower, for example, 2-inch slump or less, okay, we're going to talk about a slump test of concrete next week. Okay. We need more vibration or more compaction. However, too much compaction is also not good. It will increase the potential of concrete for segregation, which is separation of coarse aggregate and the cement paste, and also bleeding. Okay, bleeding is separation of water from cement paste, and also loss of entrained air, the good air we put in concrete on purpose. Under vibration, we're gonna have too much entrapped air, the bad air, and or even honeycombing. Honeycombing is the big holes in concrete when we do not have too much enough vibration. For small jobs, we could use steel rod. Okay, such as here, this is internal vibration, the steel rod. Okay. Okay. But not all concrete need vibration. Some high-performance concrete, such self-compacting concrete, another name for it is called consolidation concrete, does not need any type of compaction. Okay, so no compaction and vibration is needed for SCC. Right. The picture shown on the left is the vibration table. We can put the concrete cylinder on the vibration table, and it will vibrate consolidated concrete for us. Okay. Or we can put the vibration rod inside the concrete. This is for bigger job. So compaction is relatively simple compared with curing. Okay. Let's look at curing next. Right. So the reason we cure the concrete is to prevent loss of moisture from concrete. Okay. Remember the hydration, which is chemical reaction between water and compound in cement, needs water. Okay. At least 5 to 7 days. Okay, the longer the better. And inside of concrete, if the internal RH, which is relative humidity, less than 80%, the hydration process will stop. Okay, so that's one of the major reasons we need moisture at the early age of concrete. Okay, another reason is to reduce the potential for shrinkage, including plastic shrinkage and dry shrinkage. Okay, we're gonna talk about this more when we talk about shrinkage of concrete. Okay, but if the concrete lost moisture, it tends to reduce its dimension. We call that shrinkage. too much shrinkage, the concrete will crack because concrete is very weak under tension. That's one reason. Prevent loss of moisture from concrete. And another reason is to maintain a favorite temperature for a certain time. Okay. Normally around 1 week. Okay. If the temperature is too low, below freezing temperature, okay, the concrete, first of all, will stop hydration. Second of all, the concrete may crack because when water becomes ice, the volume will expand. We call that freeze and thaw attack. Okay. It is dangerous, especially when concrete is young at early age. So at early age, the concrete cannot be freeze. The temperature cannot also be too hot. In hot weather, the shrinkage will increase. If the concrete may crack, or it could cause some problems such as flash set. The chemical reaction in concrete will change due to the high temperature. The concrete may set in a few minutes. So that is also not good. And also for some other durability issues when the concrete temperature is too high, such as delayed entry guide formation. Okay, we're going to talk about it in a moment. Okay. So the objectives to cure the concrete is to prevent the loss of moisture of concrete at early age, and also the temperature cannot be too low or too high. Right. So a good curing requires 3 things. One is the moisture, the water. The second one is temperature, cannot be too low, cannot be too high. And third one is the time should be long enough, at least 5 to 7 days. Okay. So if any of these 3 factors, moisture, temperature, and time, is missing, the design property may not be achieved. Okay. This is very important. Even if you design very good concrete, you cast it perfectly, you compact it perfectly, but if the curing is not there, the strength and other property cannot be achieved. Okay. So curing is very important. All right. So effect of added curing on hardened concrete. A good curing will increase the strength of concrete because more moisture, moderate temperature, and long enough curing will ensure the hydration will go down. Okay, so we have more hydration product, the strength will be there. It will also reduce the permeability, because again we have more hydration product. The porosity of concrete will be lower, so the concrete become less permeable. Okay. We also call that water tightness, increased water tightness. Because the strength is higher, abrasion resistance of concrete will also be higher. Okay. The resistance of concrete to freeze thaw will also be higher because first of all, concrete is stronger and also it is less permeable. So water will have harder time to penetrate the concrete and do the damage. Okay. It will also increase the volume stability, okay, which means we have less shrinkage. Okay. We have different type of shrinkage, include plastic shrinkage, which is shrinkage at early age of concrete, when the concrete is still in plastic state. Or drying shrinkage, which is the shrinkage when concrete dries out, the water evaporates to the air. We call that dry shrinkage. And we also have some other type of shrinkage, such as autogeneous shrinkage, chemical shrinkage, and so on. Okay. Which again will be discussed in much more details later. Okay. But this is the benefits of adequate curing on hardened concrete. All right, so let's look at these figures. Here shows the effect of moisture curing on compressive strength of concrete. Okay, the y-axis is the strength of concrete. The x-axis is the age when we test the concrete strength. Okay. So all the four concrete, these four lines, have the same mix design. Okay, same amount of water, same amount of cement, sand, and of course aggregate. Okay. The only difference between these four concrete is the length of curing. Okay. The yellow line is the concrete in the lab, air entire time, so no moisture curing at all. The green line is in the air after 7 days of moisture curing. So this is typical curing time, around 5 to 7 days curing. And the red line is the concrete in the air after 28 days moisture curing. Okay. And the last one is moisture curing entire time before we test its strength. Okay. So again, all the concrete has the same mix design, but obviously the strengths are quite different. Okay. So what we can see here is the longer we moisture cure the concrete, the strength will stop increase at later age. Okay. For example, the concrete cured in the moisture all the time, the strength almost keep increase over a year. Okay. So as soon as stop moisture curing the concrete, the strength will stop increase almost immediately. Okay, so that's the benefit of moisture curing. Okay. The longer the better, but at least 5 to 7 days. So with increased curing time, the concrete will dry out later, which means hydration, the chemical reaction between water and concrete will keep going, will stop later. So will enhance the hydration degree and also the strength gain. And this slide shows us effect of curing temperature on strength. Okay. Again, all these 1, 2, 3, 4 concrete have exactly the same mix design. The only difference is the cost and also the curing temperature. For example, the red one means the casting temperature is 23 degrees Celsius or 73 degrees Fahrenheit. The current temperature is the next temperature, 23 or 73 Fahrenheit. Okay. All right. So the red line is the concrete casted and cured at room temperature, around 70 degrees. Okay. The blue line here is we cast the concrete and cure the concrete at 90 degrees Fahrenheit. Okay. So compare with the red line, the early age strength, which is the strength for the first week also. Okay. So early age strength will be higher. Okay. It is easy to understand because increased temperature, we increase the speed of chemical reaction. So we have more hydration product. The concrete will be stronger. Okay. However, the strength after around a week or so will be lower when we increase the curing temperature. All right. The reason for that is when we increase the temperature, the hydration speed will increase. Okay. So we have a higher early age strength. However, because the hydration product grows so fast, it will produce a non-uniform hydration product. So the chance for the concrete to have a certain type of flaw will be higher. Okay. That will generate weak zones in concrete. So that will reduce the final strength of concrete. So the faster the hydration speed, when we increase temperature, that will actually decrease the final strength of concrete. Okay, so keep that in mind. The other two concrete, the green one is we cast concrete at room temperature, but cure at 50 degree Fahrenheit. The purple one is we cast it and cured at 50 degree Fahrenheit. Okay, so both of these two concrete is cured at lower temperature. Okay, so when we reduce temperature, the early age strength will be lower because we have slower hydration speed. At early age, we have less hydration product such as CSH, so the strength will be lower. But the final strength tend to be higher compared with the control mix and also the concrete cured at high temperature. Same reason, when we have a slower hydration speed, due to lower temperature, we have more uniform hydration product. So the final strength will be higher. Okay, so this is the effect of curing temperature on the strength of concrete. Okay, so the temperature effect on curing, here is a summary. The higher the temperature, the faster the curing. Okay, the higher temperature, we have faster hydration speed. The best temperature is the room temperature, which is very convenient for us. Okay. The stronger the concrete is made at temperature around 40 degree Fahrenheit. The freezing temperature is 32, so it's just above the freezing temperature. But it is not very practical to cure the concrete around 40 degree Fahrenheit. Okay? But the stronger concrete is made at around that temperature, just above the freezing temperature. That is because the hydration will keep going on because temperature is not too low, above freezing temperature, but it is very slow. So we have very homogeneous hydration product. Okay, but the best temperature is still the room temperature because it's very practical. Okay, we don't have to do anything to achieve that. Okay. If the concrete freeze during the first 24 hours, when the water become ice, hydration will stop. Okay, so it may never be able to attain its original property. So keep the temperature above freezing temperature, keep the concrete above the freezing temperature at early age. Okay. If the temperature is very high, above 120 degrees Fahrenheit, it may cause another problems. We call that delayed etching formation. This is one type of soffit attack in concrete, which we'll be discussing in a moment. We can also further increase the curing temperature and even apply a high pressure. Okay, so high temperature and high pressure, we also call that autoclave. So that will change the chemical reaction of concrete totally. Okay, this is not very common in use, but it still belongs to special curing. Okay, we're gonna again talk about this in a moment. Let's look at how we cure the concrete. Probably everybody has saw that before. When we cure the concrete, we need to cover the concrete surface, or we apply some additional water. Okay, so that's three types of curing method. And the first one is also the best one is supply additional water, okay, by spray or pounding or immersion. Okay, so after the concrete set, okay, this is the best way to cure the concrete, provide additional water to concrete. The reason we call that best is because when we provide additional water, so we have water layer on top of the concrete. Okay, so that will ensure every part of the concrete is saturated. Okay, so every part of the concrete will keep hydrated because we have water there. Okay. The second type of curing is we do not provide additional water, but we seal the concrete, okay, by using plastic sheets. Like here, all we use, we call that membrane-forming curing compound. Here, the water spray is not water; it's just spray a membrane-forming curing compound. So it will form something like plastic sheets. So the water from the concrete will not evaporate. Okay. So the second type, sealing the concrete, is okay, but is not as good as the first type because not every part of the concrete is saturated. Okay. By putting a plastic sheets or curing compound, okay, part of the concrete is saturated, but the part of the concrete near air is only partially saturated. So that means the hydration in concrete here may not be fully developed. Okay. Compared to the first type method, it is more convenient and also lower cost because we do not need to provide actual water. Okay. But it's not as effective as the type 1. Okay. And it cannot entirely prevent evaporation. Okay. Part of the concrete is only partially saturated. Another reason it is not as good as the first one is for concrete with lower water to cement ratio, it may suffer so-called self-desiccation and a type of shrinkage, we call that autogeneous shrinkage. Okay. So when the water cement ratio of concrete is very low, below around 0.35 also, okay, because the water to cement ratio is so low, we do not have enough water. Because remember, hydration will consume a lot of water. If the ratio of water to cement is low enough, the concrete will dry out due to hydration. Okay? And we call that self-desiccation, which means the water will consumed due to hydration inside the concrete. Okay? And if the concrete shrink due to self-desiccation, we call that autogeneous shrinkage. Okay, so this is type of shrinkage caused by drying internally, not drying of concrete to the air. Okay, so this is different from drying shrinkage. So again, we're going to talk about this in more details. Right. So this is the second type of curing. The third curing method, type 3, is we use live steam. Okay, we increase the temperature by provide hot steam. Okay. This is only used in precast plant because in the field, we cannot use live steam. Okay. In winter construction, we could use heating coil or electrically heated forms or pad to ensure the temperature of the concrete will not be too low, will not be below freezing temperature. Remember, when water becomes ice, hydration will stop. When we talk about hydration, we talk about dissolve, diffuse, and precipitate. Okay, the 3 words, which means the water will dissolve ions such as hydroxide and calcium ions from the surface of clinker. Okay. So we need liquid water to do that, to dissolve the ice. When the water becomes ice, the hydration will stop because there's no dissolve, no diffuse, and no precipitate. Okay, so keep that in mind. So here shows a special curing method. We call that steam curing. Okay. So steam curing, we increase the temperature quite a lot. Okay. So here shows how we do the steam curing of concrete. So the x-axis is the time after placing the concrete. Okay. The y-axis is temperature within steam. Okay, this is in degrees Celsius. Okay, so we have a delay period. So after we finish concrete, we do not put the concrete into steam curing immediately. The reason for that is we want the concrete to achieve certain strengths. Okay, so we wait around 3 to 5 hours before we increase the temperature. Okay, so then we slowly increase the temperature. We do not suddenly put the concrete into hot steam curing. Okay, so that period, temperature increase period is around 2 hours also. Okay, so if we put the concrete in the steam curing immediately, we may have cracking of concrete. Okay, because temperature increase is too high, we may have a temperature gradient inside different area of concrete, so the concrete may crack. And then we keep the concrete temperature constant for a certain amount of time, between 6 to 12 hours. As you can see from here, we call that constant temperature period. Okay, so the temperature may be different, okay, around 60 to 80 degrees Celsius. Okay, and then we slowly decrease the temperature. Okay, again, if we suddenly decrease the temperature, the concrete may crack again. Okay, so when we change the temperature of concrete, make sure it's slow enough. Yeah, because concrete is very weak under tension. It may crack if we change the temperature too fast. Okay. For type 3 cement, which is high early strength cement, it may be longer. This is for type 3 cement. The time for other type of cement may be longer for the period 3, which is constant temperature period. Okay. Right. So here, just show us an example how the steam curing period and how the delay period before we do the steam curing affect the strength of concrete. Okay, all right. The range of steam curing around 40 degrees to 100 degrees Celsius. The best temperature is around 65 to 80 degrees. Okay, by changing the parameters, the delayed period and also the steam period, which is the parameter we discussed here, we may change the final strength of the concrete. Okay. Again, here is just an example of how these parameters are affecting the performance of the concrete. Okay, so another figure here shows us, again, how the curing temperature affect the strength of concrete. So the blue line is early 1-day stress after 24 hours. Okay. Increased temperature will increase 1-day stress. Okay. So again, that is because it will increase the hydration speed. So at 1 day, we have higher degree of hydration. So we have more hydration product. So the strength will be higher at day 1. But at 28 days, the strength will be lower. Okay. The reason, again, because when we increase the temperature, we have non-uniform hydration product. So the chance the concrete has certain type of flaw will be higher. So we have weaker zones in concrete, so the final strength will be lower when we increase the curing temperature. Okay. If we increase temperature above 60, 70 degree, it may cause a so-called delayed ethylene formation. Okay, so remember ethylene is one of the hydration product of CEE3A. Okay, so we have 4 major compounds: C3S, C2S, C3A, and C4AF. And ethylene is one of the hydration product for C3A. Okay, when C3A become ethylene, the volume will increase. Okay, so that is okay when concrete is in fresh state, when concrete is still soft. But when we have ethylene formed after concrete hardens, that expansion in volume may cause concrete to crack, and we call that soffit attack. Right? So delayed ethylene formation is a special type of soffit attack caused by high temperature. Okay, so after concrete hardens, and if with the concrete temperature is high, the ethylene may be dissolved due to this high temperature. So the aluminum and sulfate will dissolve, become liquid, and go to other part of the concrete. And when the temperature of concrete become lower, and this sulfate may become ethylene again, and that will increase the solid volume. So we have ethylene reformed after concrete hardens, so it will cause concrete to crack. So we call that delayed ethylene formation. Okay, only occurs in high temperature. Okay. Okay, so this is curing temperature. Right. Autoclaving. Okay, we put the concrete under very high pressure and also very high temperature. So this is way beyond steam curing temperature. Okay. For steam curing temperature is around 60, 80 degrees Celsius. Autoclaving, okay, here, so it's above boiling temperature of water. Okay, 160 and beyond Celsius. And also very, very high pressure. So because the pressure is very high, so the water in concrete will not be boiled. Okay, so 6 to 20 times atmospheric temperature. Okay, so we have totally new hydration reaction and new hydration product. Okay, so this is very different from the chemical reaction at room temperature we discussed in early lecture. It is only used for precast industry because we cannot bring this autoclaving oven in the field. Okay, so only in the precast industry. But the strength gaining speed is very high. We can achieve 28 strength normally in 24 hours. Okay, so the concrete will have better soffit resistance, will have less shrinkage, less creep, okay, better performance. But again, only in the precast plant, and the size of the concrete cannot be very large because we need to put the concrete into this autoclaving machine. Okay. All right, so today we talk about the curing of concrete. Okay. Remember, we should provide a lot of water to concrete for long enough time, and the temperature cannot be too high or too low. Okay, so do not let the concrete dry, especially at early age, at least for the first week. Okay, because dry concrete equal to dead concrete, which means there's no chemical reaction in the concrete when the concrete dries off. So actually, if the internal RH, the internal relative humidity of the concrete less than 80%, 80% is not very low, all the chemical reaction will stop. Okay, so keep that in mind. So after the concrete dries out, even we put the concrete in the water, the chemical reaction cannot be restarted. So we cannot revitalize concrete after it dries out. So we keep it moisture for the first week. Okay, cannot be dries out. So that's moisture, very important. The temperature is also very important. If temperature is too low, the water become ice, the concrete will crack. Okay. If concrete temperature is too high, we may have delayed etching guide formation, the chemical reaction may change, we may have fresh set, which make the concrete set in a few minutes. Not good. Okay. Also, the time of moisture curing should be long enough. Should be at least 5 to 7 days. Okay. Concrete with flash or slag, this is some mineral mixtures. It will require longer curing time because when we put flash in concrete, we have pozzolanic reaction. The pozzolanic reaction, we discussed that in early lecture, is the chemical reaction between silica coming from flash or slag with calcium hydroxide, which is one of the hydration product of C3S and C2S. Together with water, it will generate CSH. Okay. So pozzolanic reaction require longer curing time. Okay. All right. Okay. So key ideas for this lecture: why compaction is important. We need to get rid of this entrapped air, ensure the concrete will fill every corner of the formwork, no honeycombing, ensure the concrete will wrap around the steel reinforcement. Okay, so what type of kind of parameter will affect curing? So temperature, time, and also moisture. Okay, the 3 parameters. How temperature affect curing? Not too high, not too low, and how to prevent moisture loss during curing. Okay. We could provide external moisture, okay, or we could seal the concrete, use plastic sheets. Okay. All right. Okay, so that's the end for today's lecture.